Welcome to the fall series, 2023 fall series of our webinars at CTS Færøerne. My name is Rasmus Laumøller, and I'll be moderating this webinar. It's about d33 measurements, and we have a distinguished guest star that some of you will know. It's Dr. Markys Cain. And I will not spend any more time on this other than to just say that this is part of our innovation initiative, and there'll be one more webinar later in this fall. But without further ado, I'll transfer to Dr. Markys Cain. Welcome, Markys, to the webinar, and please go ahead and present yourself, and I think you can get started.
Thank you very much. And thank you, CTS, for hosting this event. It's very exciting, and I'm very honoured and pleased to have been asked to give this presentation on a subject which I'm fairly familiar with and been working on for a long time. So I'm Markys Cain, and I'm director of a small company in the UK called Electrosciences, which is down in Farnham in Surrey. My background is materials science and physics. Degrees and PhDs at Warwick University, some time spent in the US and then back to the UK. And then I joined NPL, National Physical Lab. So that's the UK's National Measurement Institute, back in '97. Anyway, I stayed there for like 17 or 18 years, building up a research group. And I met probably quite a few of you maybe that are online right now, whilst I was at NPL. And subsequently, since I've been owner-director of Electrosciences. So the background is ferroelectric materials, piezoelectric materials, functional, active materials for sensors, for actuators. And, you know, for the last, as I say, 20 years at NPL, a big piece of that is on measurement, metrology, and standardization. So I will be spending the next 40 minutes or so taking us through some, not anecdotes really, data really, actually, and pitfalls and issues with regards to how you might measure one of the parameters, piezoelectric parameters, d33 parameter. But I guess the presentation relates to an awful lot of different types of parameters which are important for piezo materials as well. So I'm going to share my screen. Theoretically, this should share the presentation mode. Is that okay, Rasmus? That's all showing okay? Looks like it is.
Yeah, you're in good shape. Perfect.
So I've got something like 30 slides here in 45 minutes, which should be fine, but I tend to chat quite a lot. So I'll be kept in good timing by Malte and Rasmus. So this is as a review. So there's a lot of details and data in here. So this is not a kind of a pretty presentation. I mean, it's fine, I think, I hope. But it's, you know, it's a presentation which is intended to be, you know, printed off or something and looked at and used in your lab, scribbled all over and so on and so forth. It's got real data in as well, some of which is owned by CTS Corp, actually, a little bit of work I did for them. But there's nothing revealing there, don't worry, Rasmus. It just shows you some of the sort of important and interesting features of doing this sort of measurement. So this is my company. This is an outline of the talk. Okay, so acknowledgements. Thank you, CTS, for this opportunity. I really appreciate it. National Physical Lab. Thank you, Mark Stewart, a very, very good friend who's actually retired from NPL, but you know, we worked together on this topic for a long time, and various organizations such as BAMAS and standardization organizations, and my good friends at Exact in Aachen in Germany, who are product tool collaboration partners. More of that later. So there's the outline of the talk. I'm going to give a background to the measurement, the sort of instrumentation that's used to make these sorts of measurements. And there are other ways of measuring this parameter, and I'll gloss over that, but they're important. I'll be using the Berlincourt, if you know what that means. It's an instrument devised really by Don Berlincourt some time ago, actually. And it's been commercialized by a few companies. One company called Take Control, and they market theirs as a piezo test instrument. A few of you might have that tool, and that's the one I've been using. And it's a good tool, it's a nice tool. I'll talk about calibration, I'll talk about artifacts or instrumental metrology, where the largest sources of error might lie in this measurement, sample effects, instrumentation effects. Some work we did a few years ago now, which is published, and I can present to you the reference point for that at the end of the talk. Pre-normative standards outcomes. So we looked at this in quite a lot of detail. I built on that, of course, in this talk and over the years. Some examples in terms of standard reference artifacts and standards. What we mean by repeatability, reproducibility, and reliability. Having worked at MPL for a few years, I can't not talk about that. And then kind of like the nature of the measurement. If you were to do it fresh in your lab, you would measure charge and you'd measure force, and you'd divide one by the other and get some kind of idea of the piezo coefficient. This piezo test machine doesn't quite do it that way, and I'll explain that throughout this talk. What about traceability? What about traceability to national standards or the SI units? Is that important even? For a lot of people, it's not, but some people it is actually, to know the accuracy, the precision of which the measurement is made. What about nonlinear effects? Or perhaps they're instrumental effects, and there's nothing to do with nonlinearity in the material after all. A lot of this work is published, and some of the work is being published, and some of it is, we don't know the answers to it yet. So, it's been around a long time, this technique, of course, but there's still quite a lot of unknowns. Recommendations, conclusions, and then one slide publicity piece about the tools that we're developing in Electrosciences, which you may be interested in. Okay, so piezo coefficients. So I'm assuming that the audience here are a scientific audience that understand what a piezoelectric material is and what basically what piezo coefficients are. There are two ways of describing the piezo coefficient or measuring the piezo coefficient. One is called the direct, and this is where you measure a charge with a force, and the other one is called indirect. Converse, it's historical, really, historical jargon, really. That's where you basically apply a voltage to the material and it changes its shape, and you measure the change in shape. That could be a displacement, and then you have a displacement, which would be picometers divided by how many volts you put on. And these two, direct and indirect, these coefficients are thermodynamically equivalent in a linear piezoelectric dielectric material. I won't dwell on that because that's a huge topic, which you probably know a lot about anyways. So the electroactive response, how much charge is generated when a force is applied, or how much strain is created when the voltage is applied. So you have a sensor and you have an actuator, okay? And we want to know what that coefficient is. How much charge can be generated when you apply a force. Quite often you want as big as possible. You want the highest sensitivity as possible. Now, in all these material systems, they're complex, of course, and they are tensor properties. They have multiple parameters along different crystallographic directions and along different polar directions. And historically, the subscripts 3.3 or 3.1 or 3.2, we typically would have two subscripts in this simplified version. The first indicates the direction of excitation. So that would be the force, for example, where we apply the force. And the second, three, in this case, they're 3.3, they're 2 3s. The second is the direction of the response. So d33 refers to an excitation in the poled direction, which is, again, historically just the way we describe these things, giving rise to a response in the same direction, in that 3 directions. So a rod that's poled in that direction, we apply a force in that direction, we measure a charge in that direction. But you can look at different systems. You can apply forces in different directions and measure charges and so on and so forth. And this is like 3.1 or 3.2. You can get shear properties. You can get lots of different properties. Tool sets. We have a piezo test meter. The picture at the top right is a photograph of a slightly old version of the tape-controlled piezo test meter. That's maybe version 1 or version 2. They're shipping, I don't know what version it is now, DM300 or something. And you can see a little sample in there as well. And you see in the bottom picture is this photograph of our system, the SP33 system, which we are launching next year as well. And they're both D33 meters. The system I'm developing has been specifically sort of like designed and built for precision measurements of polymer piezo materials, but of course it's fine for ceramics as well. Anyway, piezo coefficients. This picture on the top right shows the axis notation for piezo crystals. I won't dwell on it. You need to go and look at, you know, a nice tensor algebra book to understand these sorts of things. But the d33 and d33, this is where you're applying a force in one direction and measuring the charge in the opposite direction, in an orthogonal direction, like you would do for stretched PVDF polymer. You'd pull it and you'd have electrodes top and bottom of the sheet, and that's this direction, so they're orthogonal. And this is a 3-1 or a 3-2 if you stretch it in the other direction. And yeah, we have a tool for that as well from Electrosciences, which you can see in the bottom right. This just explains that it's not just d33 that's important. There are other properties and there are shear properties. You can see in the top right, these arrows, these circular arrows, 4, 5, and 6, that's the shear component, a twist in a certain direction. Anyway, I've talked to a lot of companies and a lot of people in measuring d33 using the Berlincourt type machine, and we're focusing on that now for the rest of the talk. This Berlincourt, we're applying a stress in one direction, a sinusoidal stress in one direction, and measuring a charge. That's the measurement. And Don Berlincourt took it, basically developed it. All sorts of issues from all sorts of different companies and universities and research groups, major issues with different values measured from the same sample. So repeatability and between labs reproducibility issues, major issues. You put the sample in once, take it out, put it in again, you get a different answer. I mean, you shouldn't do, you should get the same answer. The sample hasn't changed, or, you know, or has it? I mean, theoretically it hasn't changed, but more of that later. Every time you put a sample in, the same sample, and we get a different value of measured d33. We can't use the meter to characterize new materials, let alone to qualify the materials or samples. So sometimes people want an absolute value, maybe traceably measured, certainly accurate. Sometimes people want to see, how has this changed over time, or how has my sample changed with a slightly different composition or different electrode configuration, for example. Anyway, it all comes down to how to use this machine, how to use the instrument reliably, how to calibrate it, how often should you calibrate it, and what about longer term calibration issues? And that's what I'll be focusing on. So the rest of the talk is just lots of stuff. You have to forgive me. There's a lot of data, there's a lot of graphs, but I'll take you through some data, and then I'll drop back into some physics, and I'll take some more data, drop back into physics, and just please come with loads of questions. It's absolutely fine. And anyway, you can always find me afterwards from my website or email address. This is the piezo test d33 meter. This is how it works. You have, hopefully you can see my mouse. I'm hoping you can see my mouse. This purple thing here, this is the piezoelectric specimen. And we have loading contacts, top and bottom. Now a piezo material, when we stress it, it generates an electrical charge, okay? And we measure that electrical charge using some electrometer or some charge meter, or maybe we measure a current, okay? And integrate that to get charge. We have a static preload because we have to hold the sample into the jig, otherwise it will fall out. So we have to have a preload to hold it there. And then we apply this sinusoidal, typically, oscillatory AC force. And the AC force produces an AC charge, which we can measure. Now, so there's a whole variety of things here that affect the value that we measure, the piezoelectric value we measure. And I'll come to those in just a second. Let's finish off this diagram first of all. Underneath the bottom electrode, we have, well, we could have a load cell. We could measure load, newtons, okay? We have some sort of actuator to apply our load. And so this is, this is how it could work. We can measure the AC load in newtons, measure the charge in coulombs, and we've got a value. Now, the piezo test meter, the Berlincourt system, doesn't quite work like this, not quite. What you have is you have an AC loading system. We don't really have a load cell though. Sometimes they do actually, some of them do have load cells. The newest ones do, but the way it works is a bit differently. They have another sample underneath this piezoelectric specimen, which is a material, a piezoceramic material of known calibrated piezo response. So we have two samples, one on top of the other, experiencing the same force. If we know the piezo coefficient of the bottom one, okay, by measuring the voltage integration of charge across an op-amp. We can compare the piezo response by comparing the voltages dropped across the sample under test, device under test, and the bottom calibration sample. And of course, it works. And it's really convenient because you don't really need a load cell. But there are issues with that, which we'll come on to in a minute. These are the things we need to know then. We need to align the force through the sample. Now, we already know the sample is a piezoelectric material. It's a tensor property, okay? And its direction is important. Okay, the direction, you can see sun streaming through my window. I'm just going to change the direction a little bit there. Hopefully that's a bit better. Good. Yeah, so the tensor property is important. So we apply a force in a certain direction, and we need to know what the direction is. Okay, it must be along the line of polarization to maximize the charge coming off with that polarization in mind. We need to know what the AC force is. We need to know what the frequency of that excitation is. How is the static preload? Is that important? Can we just apply a ton to this sample to hold it in position or not? Okay, obviously not. Sample geometry. That's very important. This technique, this piezo test Berlin-Court technique, is kind of was meant to be sample geometry independent. You just put any sample in there, and you'll get a decent d33 measurement. Contact point geometry. These loading contacts, should they be flat? Should they be hemispherical? Should they be balls? What's the best option there? The ambient conditions, should we control our ambient conditions, temperature and humidity? What happens if we breathe on the sample? I mean, it sounds silly, but it's actually really important. And time-dependent relaxation. These piezo-ceramic materials or piezo-polymer materials have a time-dependent relaxation associated with them. We know they do. People have spent years measuring these sorts of things. So these are the issues which we will look at in a bit more detail. Now, this piece at the bottom here, repeatability and reproducibility. They sound the same, they are a little bit different, fundamentally the same, but repeatability says, okay, in the same laboratory by the same operator, take the sample in, put it out, take it in, put it out. That's repeatability. How repeatable is the measurement? Okay, if the sample's linear and the experiment and the system's perfect, every time you put in, you should get the same answer with experimental error, same answer. You don't. People haven't. Reproducibility, this is what's often measured using an international pre-normative sort of like round robin experiment where you take a sample or a set of samples and you share them across laboratories using different methods maybe, and to see how good the measurement is, you know, how reliable is our measurement of d33 across labs across the world. So in this little talk here, I'm just going to be talking about repeatability, of course, but I will talk about reproducibility because I'm going to describe the round robin experiment that happened a couple of years ago. It's this slide here. It's this slide here. Now, back in, oh my God, 2004, so quite a long time ago, we started looking at this at MPL. And we came up with a recommended procedure for this direct piezoelectric coefficient measurement using this Berlin-Court system. And these were the recommendations that came through. And for the most part, these recommendations haven't changed. And we spent a lot of time doing this, of course. And we worked with a lot of different organizations. And some people on this call may have been involved in this famous round robin. I don't actually have I'm not sure who's on the call, but anyway, it's likely that some of you might recognize it. And we're going to go through this in the talk, okay? Reference standards, what frequency should we be using, what sort of contacts and so on. Why do we need to use tweezers to hold the sample? I mean, why do we need to position it centrally in the electrode? Why do we care? And so on. This is important stuff. Now, in some work I did recently, and this is detail now, okay? So I don't know whether you can see this on your screen or not. In many respects, you're going to get a recording of this and you can pause it. But if you have this machine, if you have this tape control PM300, it's the piezo test machine, then these slides would be really useful for you, I hope. So I've done all this fairly recently, and it's important stuff, okay? So this is all about how you would calibrate the system, and the calibration routines for this system are certainly described briefly in the literature, in the user manual you get from piezo test, okay? But it's not so obvious how you might do it. Number one, you need a serial port, okay? And in modern day computing, how many people have got a serial port on their laptops? Or how many people even use the concept of a serial port to do anything whatsoever? Well, if you use Arduinos and so on, of course you will, but most people, well, a lot of people don't. So this is number one. You need a serial port to read in and to write back to the piezo test machine. So this is a load of detail here, okay? Now, depending on what computer you have, you can, if you have a Mac, you can use something called serial. Image is right in front of that text. Serial tool. In Windows, you can use something called real term. This allows it to emulate a serial port, okay? And these are the sorts of things in the sort of like in the colored box there on the right-hand side of your screen. You can see to set frequency, you know, it's like use S for set, F for frequency 97. To read frequency, you just type F and return. To read D coefficient, you just type D and return, and so on and so forth. And there's like a dozen or 2 dozen parameters that you can read and you can set. And there are issues with regard to setting calibration that I'll go into in a moment or two. Anyway, so once you set up the serial port, you switch the piezometer to remote mode, and you can start doing some measurements. And then, of course, you can read in every time you press D, return, you can read in the D coefficient. Okay, and that's fine. You can also then put a reference sample in, and you can measure D several times, and that will then be theoretically your calibrated value, which you then write back to the unit that your calibrated value is whatever it is, because you're using quartz, for example, or lithium niobate, for example. So this is the sort of thing that you would have to get used to doing if you have a machine like this and you want to seriously make sure that it's calibrated and you know how to calibrate it. You need to be able to do something like this, okay? You need to be able to use a serial port simulation, mode simulation, and do these sorts of things. And it's not too difficult, but it just takes a bit of time to get it set up. Okay, so, oops. So calibration issues. Now, calibration. What do we do? How do we calibrate the machine? What's the best way of calibrating the machine? Lithium niobate and quartz are 2 materials which have a very well-defined piezoelectric coefficient. They're very well, theoretically defined, actually, these 2 material systems. They're single crystal, these materials. They are piezoelectric. Lithium niobate is also ferroelectric. Quartz is not, but it is piezoelectric. And the value is, as you can see, the values of piezo coefficient are quite low. So the value of d33 in the case of lithium niobate is only 20, plus or minus 1 picocoulomb per Newton. Now, in the piezo test machine, you're not able to enter that as a reference value. You've got to have something over 100. I mean, it's just the nature of the way it's working. So there's various ways around this, and I'll go through that in a slide or two. Reversal offset issues. It's very important to always have the positive electrode. In other words, the positive charge output electrode, when you apply stress, it must be down, okay? And that's because the top electrode is either earthed, okay, and then or it's into a virtual earth, and that means you would typically experience offsets, which you don't want to experience in this case. It's very difficult in the piezo test machine, if not almost impossible, okay, to separately calibrate the system because the internal standard reference artifact, which is BTO typically, is internally housed. You can't move it. I mean, you can take it apart. It's all soldered in. It's all, you know, it didn't used to be. It used to be brass electrodes and so on, but it's all soldered in now. So it's very difficult to remove, to calibrate exactly, which means you need to use external artifacts which are calibrated in other ways as your calibrant system. Okay. So what do we use for calibration. So first of all, we need to work out what do we use for zero calibration. So zero piezo coefficient. Now, actually, this is really interesting. So, you know, you put the manual says put something in that's got piezoelectric coefficient of 0. So like a bit of paper or something, you know, or a bit of PTFE or something like that. But the problem with that is, I mean, how do you choose? What do you choose as zero piezo coefficient? It's a bit more tricky than you might imagine. And there's some research reports describing issues like this for another application entirely. And that is due to the electrostatic and piezoelectric induced charges that are generated when you squeeze a dielectric material, making certain polymers which you might think are really good, not so good. So for example, Kapton and PTFE, which you might think are really good choices of a material with zero piezo coefficient, no charges being generated when you're squeezing it. That's not actually true. These are not necessarily very good materials to choose. Polycarbonate is a bit better. Ceramics like alumina sheet's okay, and single crystal like sapphire, which is aluminum, is also very good. But you know, who's got single crystals of sapphire? And some people do, sapphire substrates. But alumina sheet might be a better option than, for example, Kapton or PTFE, which can give you an unreproducible value of 0. In other words, it's not always 0. So, what are the largest sources of error in this experiment? Now, there's loads of data here, and I'm going to drop in some physics and drop in some data that I took some time ago, and you'll see those as graphs. And I'm looking at the time, and I think I'm doing okay-ish. So, it seems to be single largest sources of error in doing this measurement, positioning the samples in the probes, between the probes, making sure that they are concentric and aligned, causes really large discrepancies in measured d33. And if, you know, soft materials are different to hard materials, okay? Different geometries are affected in different ways, okay? The larger probes, in this case, cause the largest systematic errors in d33. So you might have thought, wouldn't you, that a large hemispherical domed electrode would be ideal because somehow it's like, it seems more stable than using a point or a small diameter ball electrode. But indeed, it's the opposite the effect is. It's these larger probes cause the largest systematic errors. It seems alignment between these large electrodes or flat electrodes causes the biggest issues. And there's another issue with regards to flat electrodes I will come to. Use of too high a dynamic force. So, you know, we apply a static preload, maybe a Newton, maybe 2 or 3 Newtons, something like that to hold it in place. That's important. But also the dynamic force, the small oscillatory force we use to excite it piezoelectrically, that we then measure the piezo charge response. Now that's important. We mustn't use too high a stress because a lot of these materials, especially soft PZT and polymers, of course, are very thin materials. The materials have an inherent response to force. It's not always linear. The nonlinear response in a soft material, or the fact that a higher stress than you might expect to get from a point contact can actually depole locally the softer material underneath the probe. Even though the load is only a few newtons, the stress can be really high. So you've got that issue to deal with as well, which is why 0.1 Newton RMS is the considered recommended good practice here. Frequency. Now, depending on which country you live in, if you live in Europe or the UK, then which is Europe, then we work at 50 hertz. The mains is 50 hertz, and which means don't work on any frequency or harmonic of mains frequencies. Okay, that's really important in any electronic system, in any measurement system. In the US, it's 60 hertz, so don't work at 60 or 120 hertz. Just work a few hertz off that. It's a good recommendation as well in any electrical metrology measurement. Pyro effects. Now, I've worked with a lot of good friends. Roger Watmore. I'm not sure if he's on the call, but anyway, everyone probably knows Roger Watmore. So we worked together some time ago looking at this whilst I was at MPL. So the pyroelectric effect, this is, change in temperature causes a change in charge in pyroelectric materials, okay? So if you have a piece of PZT, which is pyroelectric, and you blow on it, and it sudden change in temperature, and it generates charge. And when you're measuring charge in the piezo test meter, the meter doesn't know it doesn't care where the charge comes from. It just measures charge. It doesn't care where it comes from, whether it's piezoelectric force induced or pyroelectric delta T induced. So bottom line is, hold it with tweezers. Don't blow on it. Don't get it hot locally. Use tweezers, yeah. And then let it equilibrate for temperature for maybe 5, 10, 30 seconds, something like that, okay? And now, because of course we're modulating at a certain frequency, and you typically will be using lock-in methods, this is less of an effect, okay? Because you're locking into a certain excitation frequency, but still, especially for pyroelectric, for polymer materials, this is a big issue. And it's essential to hold the sample with the same pre-stress every time. So this is really important. The PM300, this instrument that most of you will probably have, or something like that, has got a force sensor built in, but the previous ones didn't, okay? So you don't necessarily know the preload unless you put some load cell in there, which I've done, I'll show you in a minute or two. And then you just sort of screw the screw down one turn and say, one turn is my standard method, and that's exactly always the same. But a lot of these materials are the response is stress dependent. The permittivity is stress dependent. Permittivity changes with stress. And even though you might think, well, there's just 10 newtons, it's almost nothing, it's a ceramic. Yeah, but the stress is under the probe. Oh, yeah. Okay, it's not just 10 newtons over a centimeter. It's 10 newtons over probably a few hundred micrometers squared or something like this under the probe. So the stresses can be quite high, actually. And if you look at this graph on the bottom right, you can see real data, okay, for a soft material on the top and the hard piezo material on the bottom. And the y-axis is measured d33 value, and the x-axis is static preload in newtons. 10 newtons is the manufactured recommended preload. Now you can see that the hard material is not so dependent on preload. It is a bit, but it's not so dependent. But the soft material is much more dependent, very much more dependent, and even a few newtons difference can impact your measured value by a lot. And so the question is, well, what is the D33? And with so many instrumentation, so much metrology, you have to say as measured at so much hertz, as measured at certain temperature, because everything's temperature dependent, as measured at preload. So nearly always you will have to define your preload in any citation of your data. When you do the same experiment for quartz, you see no difference at all. So static preload, measured D33, 2.37. You see very little variation. I mean, it's just experimental error really here in the value of quartz. Now, quartz is not ferroelectric, it's just piezoelectric. So you wouldn't necessarily expect to see such a variability, to see such variation in piezo response as a function of voltage, as a function of preload, for example, applied to the material, or voltage applied to the material, and that's what we do see. Frequency. So I'm going to rattle through these now a little bit quicker because I've got the basic physics underway already. So what about frequency? Now, when we measure the measurement at different frequencies, we'd say at 97 hertz do most of our experiments. What happens if we do it at twice that frequency, or 3 times, or 50 or 40 hertz, or something like this? Well, if you have a lithium niobate material, which is a nice linear, stable source-ish, then you can measure that as a function of frequency and superimpose your data for your device under test. It might be a PC4D, it might be a hard or a soft piezo material. And you can then normalize and subtract this trend in the top graph, which is increasing piezo coefficient with frequency, subtract the lithium niobate, and you get the data in the bottom graph. And that shows you real material property response, because you've now removed instrumentation issues. The reason why the top graph is increasing value of D33 is because it's approaching resonance. At the far right-hand side, it may be a kilohertz, the system's resonating. And whenever you get close to any resonance, then of course everything out the window. I mean, everything increases typically, and you're not sure what you're measuring anymore. You also have inertial issues. You're moving large masses quickly, and you're going to have inertial charges, and you're not necessarily going to be able to equate the charges you are measuring with the forces that you don't know you're applying. Anyway, that's inertial forces. But when you do the subtraction, you can see real material property responses. Soft materials, as a function of frequency, you get a decrease in piezo coefficient, as you might expect for soft materials. Hard materials are fairly static, fairly linear. This increase here, well, I don't know what that is. Maybe it's still instrumentation. Maybe it's the fact that the machine was calibrated at 100 Hertz, and bottom line, you should probably calibrate the machine at every frequency you're intending to take measurements at. Sample geometries. This method is meant to be sample independent. It's geometry independent. You should be able to put thin discs in and big long bars. But the bottom line is it's not quite sample independent, geometry independent. And there is a difference between soft and hard materials. We have an alignment issue. We also have considerable clamping issues. And I'll talk about that in just 1 or 2 slides' time. You can see the graphs here of a mean piezo coefficient on the y-axis. And on the left-hand side, we have soft material. On the right-hand side, we have a hard material. And the x-axis is sample thickness. Now, how we did this is we obviously took lots of discs and basically laid them on top of the other. This data is published. You can get this. And you can see that once you reach something like a reasonable aspect ratio of maybe 4:1 or something like that, you end up with a fairly, flat value, non-changing value in mean effective piezo coefficient for soft and hard materials. But down here, down at the low sample thickness, you're clearly getting some material geometry related non-linearities, okay? And this is an issue, okay? Because the Berlincourt tool is meant to be, geometry independent, but it's clearly not. The issue here is an instrumental issue. The round robin I described earlier was where we sent off a bunch of samples to something like 10 different laboratories around the world and asked them to take measurements of D33 using their normal method. Then, between us all, we developed this sort of good practice in taking this measurement, like defining the geometry, defining the frequency, defining the preload, don't touch it with your fingers, getting it aligned centrally, and so on and so forth. And we asked everyone to do it again, okay, using the same set, using an identical set of new materials, and using the good practice. And you can see that the values as measured, the variation, the difference, this is y-axis, is difference from the average, okay? So the smaller the better, is improved dramatically after following good practice. So the good practice I'm describing here has been proven and demonstrated on an international benchmark. Okay. Quartz is a standard that's used across the world in any piezoelectric measurements, whether it be direct or indirect, whether you measure the displacement with applied voltage using interferometry, or a resonance method, dielectric resonance method, or using a Berlincourt type method like we're describing here. And you might ask yourself, how do I calibrate the response of my system, the PM300 system, using quartz, where the d33 is only 2.27. It's very, very low d33. Well, what you can do is you can use a certain calibration parameter on these machines called CADR relative. This is how you do it. It's also how you do it for lithium niobate. When you have any standard reference sample where the d33 is less than 100, okay, you have to use this relative calibration to fine-tune the system calibration. So if, for example, the machine gives you a 4% error, then you have to recalibrate at 1.04. You have to go CADR 1.04, and that will then give you your 4% recalibration, because you're using quartz and you know quartz, you put it in your machine and you've now calibrated it on that day, at that time, at that frequency, at that preload to quartz. And of course, it's not necessarily such a great thing to do, that is it? Because of course, most materials are in the hundreds. So how on earth do you calibrate? You know, you're calibrating all the way down at sort of like 2 or 3 picograms per Newton, but you're taking measurements at hundreds. Well, the next best thing is lithium niobate. You can do the same thing with lithium niobate, which gives you 20, so you've got an order of magnitude. And then the next best thing is, well, you have to use a hard composition piezo material that you have calibrated independently using interferometric methods or resonance methods. That's pretty much the only way of doing it. But bear in mind, you do a resonance, you're measuring it at hundreds of kilohertz. Okay, so the frequency is different. Long-term data. If you are to start reading and writing to your serial port, I would suggest you spend a little bit of time reading and plotting, okay, your data so you understand what's going on. So this is just a bunch of data. It's really useful. So I wrote, or I modified a very nice piece of code written by someone who writes C better than I do, a serial port reader. And I'm happy to share this with you. This reads in your d33 data every n seconds and runs GNU plot, okay? And you can use this on Windows, Linux, Macs, whatever you want to do. Or I'm sure you can write straight into MATLAB or something like this to read and plot in real time. You can see in this data, for example, just how stable this is over so many seconds. Okay, you can look at the stability of your system. You could also look at the stability of your environment. So this bottom graph is showing you over 37 hours, the change in temperature of my lab, the change in temperature as it warms up when I turn the heating on and as the sun goes down and so on. So, you know, this is useful information as well. But then you put something like a hard material in, okay? You put the sample in, it's a hard piezo ceramic, and look at the data you get. This is what people were talking about. This is the samples, it's just plotting data all the time. And I put the sample in with tweezers. It's giving this data up here. I twist it and it pops down here. I twist it, it's up here. I twist it. I'm twisting the sample like this with tweezers or with gloves on. Okay, I'm trying to get it centralized. I've done all the calibrations as before I've described. There we are, it's a bit better out of the sun maybe. Sorry about this, I need to get blinds in my conservatory. It's extremely sensitive. It's the same pre-stress, by the way, but it's extremely sensitive. But look, eventually I am able to get some sort of value which seems to be consistent and almost consistent back up here again when you start rotating it and so on. So this is a real tricky one. This is a bit unsolved still. How do we do this at the moment by eye? We're just rotating it, doing it by eye. Look at soft materials. It's maybe actually a little bit easier than a hard material. We start off in a completely, so this is 330 to 370, by the way, this axis, if you can't read it, picocoulombs per Newton. It is, you know, big changes, but you can see as I'm twisting it, I am reaching this asymptotic value. I give it another twist just to annoy it. It comes up here, I give it another twist and it comes back to this same value. So the question is, well, you know, what's the best practice here? Well, we're looking at the mode, aren't we? We're looking at kind of the most common value over a period of time. Because you might say, well, this is constant, and I might have just measured it here and it seems absolutely fine. But when I do it a few times, this is clearly the value I should be set at. So this is a real problem still. Now we look at the same sort of thing with the soft material. This is now 10 millimeter diameter and 10 millimeter high. So this is a different aspect ratio. And this is a little bit better. You can see there's massive changes as I rotate it. As I'm rotating it here, it's going down to -600. That's because the sample's electrically disengaging with the contacts. That's the only reason. Average or take the medians. I'm suggesting take the most common reading. I think you'd require binning of the data to make this statistically valid. It is a real problem though still. But in doing these sorts of measurements, in polling, not polling a ceramic, in taking loads of measurements, streaming data, this is the way you can actually really start to look at the consistency of the measurement. And we do the same thing with the 4D material. And just look at this. This it's all over the place. And only eventually, after we are confident that it's had plenty of time to equilibrate, that we're doing lots of different rotations, can we see, okay, we are reaching some sort of value which is consistent. It's going back to that same value. But you can see there's a lot of data here, and there's a lot of unknowns still. Now, I don't have much time left because it's 1:45. I want time for questions. There are time-dependent effects on all these ferroelectric materials. As you know, the materials are time-dependent. There are relaxations associated with them. Remember, these materials are poled electroceramic materials, which means they've been through temperature, high voltage, and poled, and they've been aged. Okay, so you'd only ever buy these materials after they've been aged so many months on the manufacturer's shelves, for example. And the aging looks like this. This graph at the top, this is time on the x-axis, and this is piezo response. And the manufacturer will pole it, and it will age, and they'll sell it here, typically. So, manufacturer, please tell me if I'm wrong, but this is pretty much what you need to do. And we're suggesting here is that every time you start this experiment afresh, we are starting the relaxation from fresh again. Okay, in other words, we're starting the aging process again. Remember, we're applying a preload. So it's the preload which is initiating this aging relaxation process. It's much more significant for a soft material compared to a hard material. But what does this tell us? Okay, good practice here would be to make sure that we understand this, and we would apply, well, it means really, I suppose, you're not able to take the measurements very quickly. You would need to make sure the sample's been in there for the same amount of time each time you do the measurement, and that any relaxation or aging, if that's what it is, has been manifest and is spent. There are differences in soft and hard materials, of course. We know that the permittivity of hard materials increases under stress, but for the soft materials, permittivity decreases. Now, permittivity, the ability of a material to store a charge, material property, is an important parameter which increases typically with increasing piezo response, as we know. So when we consider load contact probes, we know that increased contact area decreases static stresses. Okay, so increasing contact area, we're going from a point contact to a flat, therefore the stresses are going down. Now the soft material, the measured d33 increases, and that's this graph down here, this plot down here. Okay, but for a hard material, the measured d33 decreases, which is interesting, isn't it? But it's probably related to the fact that permittivity is changing in this way. Very thin samples exhibit proportionally more regions under where a high static stress. Okay, so when you have a very thin sample, like a thin film or a thick film, or a very thin, like 0.5 millimeter thick ceramic piece, then the region of that material which is experiencing a high stress and therefore possibly high depolarizing stresses is increasing as a proportion of the total volume of material. So we might see a real impact of that when we measure the property of that material with different stresses. And we can see this here, little FEA modeling that we did. When we say, okay, so we have a piece of ceramic down here. Okay, this is just half of it. And we have a dome-shaped contact here, and we're applying a pressure. I'm looking at the FEA plot down at the bottom, by the way. And we're applying a pressure with this contact here. And we're saying, what's the difference in the simulated d33 as a function of basically the size of this probe, okay, compared to the size of the whole material. So the radius, the percentage of the radius that's clamped. Now, when we apply a load under this hemispherical domed electrode, now that's not moving. That X and Y, it's not moving, which means when it's in contact with the sample, especially if the sample's a thin film, then that part of the film is clamped. It's not able to move in X or Y. It wants to move in Z and generate a charge, but it can't move as much in Z as it wants to because its X and Y is clamped. Okay, this is a big issue in any thin film work, thin film piezo ferroelectrics. Everyone on this call probably knows that, but it's also an issue here. Therefore, this effect here of the d33 that you might measure as a function of how much you're clamping that piece of material In other words, what's the region of stressed area of stress material? When the radius of that material clamped is very small, in other words, you're using just a point contact, okay, the stresses are high for sure, so we have a stress-induced issue, but the clamped region is very small, which means our actual simulated value is what you'd expect from the book value of D33 of these materials. But as we clamp this sample more and more and more using a wider and wider and flatter punch, we reduce the effective piezo coefficient all the way down here. Look at the effect of that. It's enormous. It's absolutely enormous. Now, in the Berlincourt method, we're somewhere here. We're not over here. We're not putting a great big flat plate on the sample, but we're somewhere here, which means we have so many things going on. We are clamping the X and Y direction that the sample wants to move when it moves up and down under stress by virtue of the geometry of the probe. Geometry of the probe, which is why we suggest not using flat probes or flat punches, and it's why we suggest also using small diameter electrodes. What about off-center? Now it's 7 minutes to 3. Oh my gosh, I'm so sorry. I think I've got like 2 slides left, but this is really important because there's so far been nothing to describe why is everything so sensitive to being off-axis. This is the biggest issue, isn't it? It seems it's clamping for sure. Maybe it's nonlinearities with stress for sure. We know this with permittivity. I've described that. But why are the parameters so dependent on just how perfectly you align it? Okay, and this attempts to explain it. Now, this is my considered opinion. I'm not saying I'm right. Okay, I would love to hear feedback and responses on this. But if we look at these are lovely pictures, aren't they? If we look at this plot here, oh, I should have referenced it. I'm sorry. This is Dave Hall's work and other people's work. Beautiful work of d33 against angle. This angle of force going from 0 to 90, 0 to minus 90, like this. Okay, and for different compositions PZT. Now, a lot of people say, yeah, but you know, even like 10, 20 degrees off axis with a 50% PT, in other words, the composition of PZT, the value is fairly constant, it's fairly static. It should not be sensitive to misorientation in the way we've shown it. But we've seen sensitivity, haven't we? We've seen it, massive sensitivity to the way it's being held. And perhaps it's because our compositions aren't 50%, our compositions are 60% or 70% or something else, or maybe we're not on the tetragonal, we're on the rhombohedral side of the MPB, which means we do have this sensitivity, this drop-off in response. This is D33 on the y-axis, as we apply stresses in different non-orthogonal directions to poling. Okay, so this is my current understanding. This is, I think, really important. And how do we deal with that? Oh, I'm going to skip over this. I calibrated the load on the Berlincourt system. You need to do it. It's got to be done. You can get these load cells, digitized digital load cell systems. I can do that. How do we go about maybe concluding calibration summary? We've calibrated the static preload. Good. We have a D33 response calibrated for quartz and lithium niobate. These are fairly standard, robust, solid materials. Sure, we can go to higher piezo coefficient materials. Might even go to single crystal materials, which are possible. Well, the relaxors, they're not actually that stable, are they? Anyway, and we can use that quartz and lithium niobate to recalibrate the standard reference samples that come with the Berlincourt tool. Okay, and we do this regularly. We have to do this on a regular basis. I would suggest almost each time we use the equipment, if you turn it off, you'd have to redo this. And the reason is, I think, not always is the calibration data stored on the on the EEPROM system, on the Berlincourt system. But look, apart from these dynamic forces, static preloads, we've gone through that, optimum work conditions, that's in good practice. How do we align the sample? A little conversation that I had with my friends at CTS Corp, we were discussing all sorts of things. And, you know, maybe there are ways of using sort of automatic alignment concepts, like this is an iris, an aperture on a camera. Okay, so it's always concentric. And so we need to centralize our sample and the force, and we need to do it quite accurately. So how would you go about doing that? I think this is a neat little option, something I'll be looking at. I'll let you know how it goes, probably on my website or something like that. But I think this is kind of the next step in evolution of this tool, unless you use other tools, such as I'm going to show in a few minutes. This is a summary. I've got 4 minutes to the hour. I'm going to go through these. We've talked about it, about the loads, AC loads, sample geometry, loading probes, time dependence, measurement frequency, and calibration. Okay. Environmental issues, very important, the pyroelectric effects. Okay. References. You have all these references, plus the standards which a bunch of us wrote, including the European VAMAS report that I've cited already with this information on. And you have a copy of this presentation. So I'm hoping this is going to be really useful to you. This is my last really busy slide. This is just an advert for my company, really. So, you know, I mean, I've been developing these tools now, knowing that there are certain metrological issues associated with measurement of d33. So I've developed this tool here, which is a metrologically robust d33 measurement tool using a different principle than what I've been describing. In the top right, there's a d31 tool for measuring polymer materials. And for sure, you know, we can model these issues using COMSOL and so on at Electrosciences. And we've got 2 other tools that we're developing, a laser intensity modulation system, which is measuring polarization through thickness. Very exciting tool, and I'll be working with Exact on that as well, actually. And then this tool here, SB-Rig, this is a tool I developed along with my colleagues at the Office of Naval Research, the Naval Research Labs in the US, and University of Liverpool and the Xmas Beamline in Grenoble. This is a tool that we can measure in situ operando properties of piezoelectric materials, whilst also measuring the X-ray diffraction or spectroscopy from said materials. And I'm done, and I'm so sorry I've used up our question time, but I can hang on for a few minutes if needs be.
Thank you, Markys. Appreciate the talk, and I guess the conclusion is that it's very, very difficult. So I'll ask everybody to write questions in the Q&A, and in the meanwhile, I have a question.
Yeah.
So we had a problem where we were trying to measure d33 on a composite material, so a polymer, a ceramic powder suspended in a polymer material, and this case was KNN. And what we observed is that it was extremely sensitive to humidity, and we know KNN is sensitive to humidity, but what we observed is that over seconds, when the material absorbed humidity, the d33 increased significantly, you know, a factor of 2 almost. And I don't know that we really understood the mechanisms, but maybe you can speculate on that.
Yeah, that sounds very interesting. So I can't imagine the d33s increasing by a factor of 2. I mean, because we always have to work out, like, you know, what is the measurement? The measurement is it's measuring charge, and as I said before, it doesn't care where the charge comes from. It's just measuring charge. It'll come down to, you know, how it's doing the measurement. Is it using lock-in methods or is it not? So anything absorbing moisture or water will also be changing its temperature. So the pyroelectric effect will play an important part there. So if you were just to plot as a function of time, the charge with time, then you would see these effects. You would see the pyroelectric response. You'd be able to do all sorts of experiments to differentiate pyroelectricity from piezoelectricity, for sure. And any issues with regards water, moisture, humidity absorption, well, so you'll get charge leakage. So I would imagine you'd see a reduction in charges, but maybe it manifests it differently. But you'd also expect to see a swelling of the material, probably. You would normally get a swelling of polymers with water absorption. I think you nearly always do. If you get a swelling, you'd get an additional stress, probably hydrostatic stress on the piezo particles, which would impact your measured value of d33. I think that's going to be a mixture of decoupling the measurement of charge in your system, which means you might have to use a slightly different system to do that decoupling. because it's coupled so well to the sample that's in series with your sample in the piezo test machine. That's the problem with that tool.
Okay, I think we'll go on to the questions now from the audience,
yeah, sure.
because we have a lot of them trickling in here. So, and please be succinct, Markys.
I'll do my best.
So Nikolai Feidelhansel, my colleague here, is asking, you mentioned linking to SI units. Can you quickly touch upon this, especially with all the uncertainties just mentioned?
Yeah, oh, that's a huge topic though, for sure. Yeah, so if you wanted to measure charge, then you would have to work out how you would link charge to the SI units of it's very likely you'd want to do it as a measurement of current. So you'd want a current standard. So you go to MPL and ask them for their quantum current standard. So they would have a halfway house, an interim standard reference to their current standard, to the SI unit. So when I say SI units, it's about traceability. You need to be able to show how your measurement you just made using your system through its calibration route is traceable to the SI unit national standard at your national lab. May not be NPL, whatever your national lab is. Okay, in Denmark it's RISO, I think. Anyway, so there's that's how you would do it, and you do the same for length and for forces. Dynamic forces you can't really do, by the way. There's still really no dynamic force SI, kind of like traceable SI methodology if you talk to force specialists at the national labs. So that's what I mean by SI units.
Okay, thanks. We have one more question here. Do you have any tips for someone making a d33 on nanowires using AFM?
So I actually work on a European project called Nanowires. Maybe this is one of my colleagues. Yeah, so I'm gonna actually.
This is Nilesh Badwal. I hope I get the pronunciation.
Yeah, hi. It's a really tricky one because of course, so AFMs, yeah, these are notoriously difficult to calibrate and to create traceable measurements of charges and forces. The Nanowires Consortium have developed, and also there's another European consortium looking at standard current and standard resistance measurements at the micro and nanoscale. So yeah, maybe if they can drop me a line, I can point you in the direction of how other people have tried to make traceable measurements of forces and electrical currents using AFM methods. But it always comes down to point contact issues. It always comes down to mechanical electrical contact issues, nearly always.
Okay, thank you. Maybe there's a collaboration there. We have Andreas Habeland. Can you briefly comment on methods and pitfalls for measuring D51?
Yeah, so this is even more difficult, isn't it? I haven't focused on D15, the shear coefficient, at all in this presentation. The methodology is fairly similar. You're measuring, you're measuring charges and you're applying shear forces. Okay, so in this case, you need to be able to construct a device to hold your sample such that you can create perfect shear in the material. And this is difficult, of course, because you will necessarily thereby clamp the material when you apply shear in something like this. Okay, so you're applying shear like this and you're measuring charge like this, for example. Now there are tools you can think, at least, that you can buy to create such a geometry to apply shear, but I'm less familiar with them, and I'm not so confident that they apply pure shear. Any off-axis orientation will have quite a profound impact on the shear response you measure. If you remember the graphs, the pretty 3D volumes I showed you, when you look at the 1.5 or the other shear 4.2, for example, the other shear properties, you can see just how just how sensitive those values are to misalignment of shear. So in good practice, you need to devise a methodology, maybe we can talk, I don't know, to, as well as you possibly can, define the shear in that component. And then you have to do some modeling, because you will necessarily clamp the sample in the 1-2 direction to apply that shear, very likely. Sorry, that's not terribly, I'm not sure how helpful that is, but anyway.
No, I know that's a challenge we have and are trying to address at CTS as well. So thank you for that question. We just got one more coming in. That was just a comment. Again, thank you from Andreas. All right, I think we'll end it there. Thanks a lot, Dr. Markys Cain, again, for doing this. It was very interesting. It's my personal opinion, but I think I can speak for a lot of people. And feel free to contact Markys. I hope that's okay, Markys,
yes,
on this topic and others.
Very happy to chat.
And we'll stop it here. Thank you very much.
Thank you so much. Thanks, Rasmus. Thank you so much, everyone, for listening to my talk. I appreciate it. Thank you.
Thank you.